Chapter 27, Current and Resistance. All the discussions that we have done for 1C so far involves what's called electrostatics. And that means we did not consider the case when electric charges are in motion. In other words, we consider the charges as just fixed points. Now, in a real electrical circuits, we do want these charges to move. So therefore, starting from this chapter, we're going to consider the case when the charges are in motion, and when that happens, we say an electrical current is formed, and when the current flows through a circuit, it will encounter some resistance. So that is why we're studying current and resistance. Again, an electrical current or current is a flow of electrical charges. And to define it more precisely, let's consider a situation like this. Suppose we got a bunch of positive charges, okay, and they flow through a certain region in space. Let's isolate a certain cross-sectional area A. This is a certain cross-section area, and we allow the charges to flow through this cross-section area. And let us count how much charge flows through this area. Okay, let's say the amount of charge flowing through this area over a certain time interval is dq. If we consider a very small amount of time interval, then the charge going through it is a very small amount, which we call dq. Now, one wishes to know how fast charge will flow through it. What is the rate which through it? So, and we divide dt takes for this much charge to pass through. Okay, and you notice that in this definition, the actual area of this cross section is not in it. So it's just the rate at which charge flows through a certain amount of area, dq over dt, and that is defined as electrical current I. Okay, and the SI unit of the electrical current, of course, is 1 coulomb over 1 second, and following the convention we've been using all time along, we're going to call it by the name of a physicist. And in this particular case, the name of the physicist is Ampere, a French physicist, and you will see why he gets this recognition, because there is something called Ampere's law, which will come up later. So 1 ampere or 1 amp, or simply 1A, okay, is defined as 1 coulomb per second. That is the prime SI unit for electrical current. Now, let's see, based on this definition, how do we calculate the electrical current based on such microscopic quantities such as how fast each charge move, and how many charges are there per unit volume, that sort of thing. Let's say this is a wire, okay, and in that wire we got positive charges flowing in a certain direction from left to right. For simplicity, let's assume that they all have the same drifting velocity, Vd. D, again, standing for drift. You know what the term drift means, right? It basically just moves, it moves from one place to another, in this case due to the presence of an electric field, so it goes from here to there. They're drifting in this direction. Suppose we look at a certain charge. It's got a charge Q, okay, it's got a charge Q. That's the charge carried by each one of them, and is moving at a drifting velocity of Vd. Alright, that is one charge. Now, how many charges are there? Well, that depends on the volume that we're considering. Now, if we want to find the electrical current, we must count the total amount of charge dq that flows through this certain area, cross-section area, over time dt. Remember, each charge moves with a speed vd. Now, over time dt, how many of these charges can flow through it? Well, if a charge is way down there, it will not be able to make it to here by the time dt, right? It has to be close enough to this cross-section so that it can actually make its way past through this cross-section. So the question is, how far can this charge be from this and still make it over time dt? Well, if the speed is vd, then it can move a distance of vd times dt over a time interval dt, and therefore if a charged particle is right here with a distance of vd times dt away from this intended cross, can barely reach this point, okay, reach the desired cross section. And if a particle is further away, it's here or here or here, then it will not be able to make it that tells us that all the charges that will successfully pass through this cross-section over a time dt must exist within this within this region. And this region is the cross-sectional area A, and it's got a height of Vd times dt. So it's a cylindrical region. Okay, what is the volume of this cylindrical region? Now that would be Vd times dt, which is the height, and then times the cross-sectional area A, right? That is the volume. And how many of these drifting charges are there within this volume? Well, if we know the amount of charge per unit volume, okay, actually the number of charges per unit volume, that is called the number density. Okay, please distinguish this from charge density, because we're only counting the number per unit volume. We're not counting total charge per unit volume. Okay, suppose that number per unit volume is n. You multiply n by the actual volume between here and there. What do you get? You get the total amount of charge, of such drifting charge, right? Let's say a million or billion, whatever. You get that number, right? You take that number multiplied by the charge carried by each one of them. That's Q. And then what do you get? You get a total amount of charge, drifting charge within this region, and all these charges will successfully drift past this cross-section, and therefore, by definition, that is just dq, right? The amount of charge passing through. And all you have to do is take that dq divided by dt, and what do you get? You will get the electrical current passing through it. Okay, so I is now, due to the definition, q over dt. Q N A Vd times dt, and you divide it by dt. You see dt and dt crosses out, and you're left with Q N A Vd. That is how we find the electrical current based on such microscopic quantities, such as the charge carried by each mobile charge, the number of charges per unit volume, and how fast they move. Okay, how fast they drift. And A is the cross-section area. Now, if everything else is the same, the greater the cross-section area, the greater the amount of current going through. Of course, that makes sense. Now, if one take this A and we divide it over, okay, I over A, what do I get? I get the current per unit cross-section area, and that has a new name. We call it the current density. Okay, J, defined as current density. Okay, current density. Now the current density can vary from point to point, but if we're looking at a certain point where the local charge number density of charge is n and the local drifting velocity is Vd, then one can easily say that for that particular location we have J equals to Q N Vd, right? And you can see J changes from point to point if Vd changes and if N changes. Okay, in a region where there are a lot of charges per unit volume and the charges move very fast, you can imagine there is a greater current density. Now, the direction of the current flow is along the same direction of Vd, assuming Q to be positive. Of course, if Q is negative, automatically you get a negative sign, so the current reverses. All right. Therefore, if I put a vector sign to bring this Vd back to the full vector form, I will get a vector current density. Okay, so the current density is a vector quantity. It's a vector quantity. And it is equal to Q times N times Vd. Now, N is relatively simple to calculate. We'll see an example for that. But what about Vd? How does one find the drifting velocity of these mobile charges? Well, let's see how we might be able to do that. Before we attempt to calculate Vd or estimate Vd, let us first make sure we understand the concepts. It turns out there are three different speeds, okay? Three different speeds of electrons or any charged particles in a conductor when it comes to forming electrical current. One is called the signal speed. And what is that? Well, if you have an electrical circuit, okay, and there is a circuit breaker, a switch. Now, when you flip that switch so that you close the circuit, then immediately, you establish a current throughout the entire circuit, right? Because the fact that you close the switch this signal will propagate through the entire circuit very, very quickly. As a matter of fact, at the speed of light. Okay, I don't know if you know that piece of history, but you know, the Hoover Dam, which of course was built over Colorado, on Colorado River. The first time Hoover Dam operated, it was operated by a switch flipped by President Roosevelt in the White House, and we're talking about, you know, a couple of thousand miles, and yet the moment he flipped the switch, the operation started. So it's because the signal traveled at the speed of light. Okay, so that's a signal speed, and that is not what we're talking about here as far as drifting speed. The second speed we're looking at is so-called random motion speed. Now, what does that mean? Well, every one of these mobile electrons, okay, electron here, electron here, electron here, electron here, even if there is no current, you know, in the absence of a net electric field, there is no electrical current, there is no net flow of electrons from any place to any place else. They still move randomly, okay? They still move randomly, and that is partly because a piece of metal usually has a finite current, finite temperature, which is not at absolute zero temperature. As you know from physics, when be anything that is whose temperature is above absolute zero, there is a certain amount of random motion involved. So these guys move randomly, but since they move in each way, they do not create a net direction of current flow. But it turns out that even if you do not consider any finite temperature effect, okay, at any temperature, even at absolute zero, it turns out that these electrons in the real piece of metal still move at very high speed in random directions. The random motion is inherent. You cannot totally eliminate it. It's always there, whether or not there is an actual current. Okay, whether or not this piece of metal is exposed to an electric field or not. And these random motion can be pretty fast. As a matter of fact, you will learn in physics 1D, okay, as a preview, you will learn in physics 1D that even down to absolute zero temperature, on average, these electrons will move at speeds around 10 kilometers per second, okay, per second, not per hour. All right, so we're looking at a very, very high random motion speed, whether or not there is an electric field. This is to be distinguished from the drifting speed, which is an organized speed in the same direction, powered by an external electric field. Okay, no matter how fast random motion speed is, it is not going to disrupt, it is not going to cause any net current flow because the direction is random. So that is not what we're talking about. This is not what we're talking about. The drift speed, that's the third speed. That is what we're talking about. Okay, now we know this is signal speed is its speed of light, is extremely fast, and this is also very fast. We're talking about, you know, a few miles per second. And what about drift speed? That is the speed that is actually responsible for forming an electrical current, right? How much is that? What is the order of magnitude? Well, we can do a little estimation here, shall we? Let's go back to the previous page where we had the formula for J, okay? Current density, right? So current density, Q and VD. Now, in the case, let's say we take a real piece of metal, say copper, okay, for copper. And let's look at an actual copper wire with a certain cross-sectional area A, okay? Certain cross-section. Let's say the current flowing through it is I. And then, of course, the charge, the current density will be I over A, right? And that equals what? Q and VD. Q is the charge carried by each of the mobile electrons. So it's actually E. We're looking at the magnitude only, okay? Times N, the number of free or mobile electrons per unit volume, and then times VD. Okay, I'm just copying this. Now, you can see clearly that all I have to do is to find I, find A, find E, find N, then I can find VD, right? I can solve for VD. Okay, let's look at a numerical example, a typical value, okay? Let's say we have a current of 1 amp. That doesn't sound like much, right? A current of 1 amp. So I, about 1 amp. And the area A, okay. Let's look at a typical wire, all right? Let's look at a typical wire, and let's say this wire has a certain cross-section area of 1 millimeter by 1 millimeter. Does that sound like a reasonable value? Yeah, it's pretty reasonable, right? So it's 1 millimeter by 1 millimeter. Of course, you say, oh, it's pi r squared or whatever, but you know, we're just estimating, okay? So let's just say 1 millimeter times 1 millimeter. we're looking at 1 millimeter is 10 to the negative 3 meters. We're looking at 10 to the negative 6 meters squared. Okay, so I over A, the current density. This over that, we're looking at what? About 10 to the 6. Okay, amp per meter squared. That is the current density, J. All right, let's write down E. We know what E is. E is about 1.6 times 10 to the what? Negative what? 19 coulomb, okay? 19 coulomb. That's the elementary charge carried by each electron. In order to find VD, let's estimate N. Now, this takes a little bit more effort. What is N again? The number of free or mobile electrons in a piece of copper metal per unit volume. Okay, we know that each copper atom contributes one free electron. Okay, so we're looking at really the number of copper atoms per unit volume. How do we know that? Well, it turns out all we need to know are two things. One is the so-called molar mass of copper. What is the molar mass of copper? How many grams of copper will make up 1 mole of copper atoms? And we know that equals about 63.5. Okay, so every 63.5 grams of copper has 1 mole of copper atoms in it. Okay, 1 mole of copper atoms in it. And each mole, of course, has Avogadro's number of copper atoms, and that's about 6.0 times 10 to the what? 23, right? Per mole. So from these, we can figure out for every 63.5 grams of copper, I have this many copper atoms, in other words, this many free electrons. The second data that I need is the so-called density of copper. You know, just how much, what is the mass per unit volume of copper, and that's about 8.9. Okay, about 8.9 grams per centimeter cubed. Okay, now within every centimeter cubed, I don't have a whole mole because a whole mole takes that many grams, but I do have 8.9 grams. How many moles would that be? Well, that would be 8.9 divided by 63.5, right? That's the number of moles within a cubic centimeter of copper. But each mole has this many copper atoms. 6.0 times 10 to the 23. In other words, this many free electrons, because each copper atom contributes 1 free electron. Okay, so this is what? This is the number of free electrons existing in every cubic centimeter. All right? So what is the number density then? The number density N of mobile charge in a piece of copper is just this. All right? 8.9 divided by 63.5 times 6.0 times 10 to the 23. Okay? And if you work this out, it turns out to be roughly 8.5 times 10 to the 28 electrons per meter cubed. I change it from centimeter cubed to meter cubed. Okay, all you have to do then is to plug this into here. Okay, and you have I, you have A, you have E, you have N now. Let's solve for VD. Okay, so VD equals to I over A divided by E N. Okay, let's plug in the numbers. Let's see what we come up with. Okay, I over A is about 10 to the 6. Okay, I'm using prime SI units, so let's ignore the units because we've already written it in prime SI unit. Everything's going to just cancel out neatly. 1.6 times 10 to the 10 to the negative 19 times N. N is 8.5 times 10 to the 28. Wow, look at that. Negative 19, positive 28. Now if you move that negative 19 up over, you get positive what? You get positive 20. But here is a negative 28, right? 10 to negative 28. So overall, if you work this out, you find that you're getting a very small value. VD, if you did this calculation, you find the answer is around 10 to the negative 5 meters per second. Wow. Does that surprise us? Well, there's a very, very small value. Of course, we're estimating. There is an example 1 in a textbook, and over there, the only difference is that they use 10 amps and we use 1 amp. There's not much of a difference. But you will come up with a similar estimation, also a very, very small value. Okay, a very, very small value for the drifting speed. Does that surprise us? It is a lot less, okay, than the random motion speed, which is several miles per second. Here is this many, okay, it's less than a millimeter per second, okay. So it's gonna take, if you want to crawl at this speed, you want to crawl just a couple of centimeters, it's gonna take you an hour, okay. It take you an hour, and it's even further less than the signal speed, which is the speed of light. How come such a very, very, very insignificant speed is responsible for the actual current that we can measure? Well, the fact that the speed is very small doesn't tell you the whole story. There is an important difference between drift velocity and random motion velocity. And notice I said velocity, not speed. And what is that? And that is the drift velocity is in the same direction for every one of these particles. Okay? So basically we're saying that on top of the random motion, every one of these particles, every one of these electrons also has a tiny but organized drifting velocity. Okay? Drifting velocity in the same direction. Even though this velocity is tiny, they do not cancel out among these electrons because they are in the same direction, unlike the random motion velocity, which is in every possible direction. And it is such a very slow velocity that is actually responsible for the macroscopic current that we can measure. Okay, so here is a myth that a lot of people may had in mind, and that was that the electrons, in order to form a large current, the electron have to move very fast. Their very fast speed is only the random motion speed. Okay, the organized speed responsible for the current is actually very small, but it's still very. It can still add up to a significant current because there are so many of these electrons, and they move in the same direction, and that's what's responsible for the current.